Hey physicists, strap your boots on. We're going to talk about electric fields today. So we finished up Coulomb's law. Remember that Coulomb's law was by Coulomb, who lived around the time of Sir Isaac Newton, and he came up with the forces that attracted or repelled two different charges, whether they were positive or negative. Now, when we talk about electric fields, remember that at the time there was this whole kind of interesting contact versus non-contact debate, because up until that time they thought, well, every force had to be literally, the two objects had to be touching, otherwise this would be demonic, or it would be very like superstitious that something could put a force on something else without actually touching it. And so the folk in the 1700s have trouble wrapping their brains around that non-contact forces. They thought that it was a very superstitious idea. And so whenever we came up with this non-contact force, Michael Faraday decided to call this a field. It's the area around an object that affects other objects. The area around an object that affects other objects. So a non-contact force always has a field associated with it. It's the area around an object that affects other objects. So when I talk about the gravitational field, it's the area around a mass that affects other masses. When I talk about an electric field, it's the area around a charge that affects other charges. When I talk about a magnetic field, it's the area around a magnet that affects other magnets. So field is the area around an object that affects other objects. And then a test charge is the charge, if this is my original charge and it has this field around it that is affecting other charges, the test charge would be the charge that I bring and I put in that field to see how is that charge affected by the original charge because it's in that field. Okay, you can think of this very, very similar to gravity. If we put this in the analogy of gravity, so you have the planet and then you have the moon orbiting the planet. Well, very similarly, when we talk about an atom, we have the proton in the center and the electron is orbiting the atom or the nucleus. So the gravitational field was by Newton. Newton said that the moon is affected by the Earth's gravitational field. The electric field then was determined by Faraday. So Faraday is the one who came up with this idea of electric field. So the satellite and the electrons they both experience what we would call field forces or non-contact forces. So you remember the Newton's law of gravity, gmm over r squared, and remember how we lumped together this gm over r squared, and we said that this is the area around an object that affects other objects, otherwise known as a gravitational field. So that's our A value. And remember that looks very similar. It fits very well into Newton's second law then, F equals ma. So what is this field called? It's the acceleration or gravity, g, and that is really your gm over r squared. Well, we can do something very similar with the electric field where we can take this kqq over r squared, we can lump together our kq over r squared, and that becomes our electric field. And so we end up with something similar to Newton's second law, but for electricity. The force is equal to the field times the fundamental value. So the field is your electric field, and the charge is your fundamental value. So what is the field in this case? It is the E value, and it could also be in an equation that is kq over r squared. Now remember that this uppercase q, sometimes you would see these as q1, q2. I like to do uppercase and lowercase just because mentally it's easier for me to think that in this equation, E equals kq over r squared, that big Q is the Q that is putting out the electric field. It's the field is coming from that big Q. As opposed to the little q up here, that little q is going to be the test charge or the charge that's placed into the field of the big Q. So when you look at that, there are two different equations then for electric field. We have the force is equal to the field times the charge, and here's sort of the breakdown of each of those symbols. And then we also have that the electric field is kq over r squared, where q creates the field. K, remember, is that constant, 9 times 10 to the 9th, and r is the radius away from that charge. So here is a picture. What does this look like to you? I often get some really random answers, like it looks like Star Wars going into, or Star Trek going into warp drive. Star Wars when they go into the light speed. It could be the tip of a pencil, so you're looking at the lead. It could also be a tunnel where you're looking down a tunnel into a black hole or something. What we're really looking at is sort of the idea of an electric charge. Now, technically, it's not a charge. This would be a magnet, and you're seeing the magnetic lines, but it is analogous to the electric field where we would have our charge in the center, and then these lines coming out of it are going to be our electric field lines. So the rules that we need to know for drawing electric field lines, there are 3 of them. The line always tells the direction that a plus charge would go. Because remember, whenever they first did this, they thought the plus charges were the ones that moved. So most of our convention is with a moving plus charge. So if I were to take and I put a plus charge, see if I can draw a plus charge here, what will two positive charges do? They will repel each other. So in other words, it will push that plus charge that way, and that's why the field line goes that way. If I take and do the same thing over here where I say, well, what if I put a plus charge here? What will the plus charge do to the negative? They will attract, so it will pull the plus charge toward the negative, and that's why the arrow is going into the negative. So out of positive into negative, out of positive into negative, out of positive into negative. And we'll use this a whole bunch of different times, so you got to memorize this, out of positive into negative. The lines always come out of perpendicular to the surface. So the second one is they always come out perpendicular. You would never, ever, ever see, so I'm going to put a big, this is not right. You would never, ever see where the line comes out like this, and over here it comes out like this, and over here it comes straight out, and then down here it comes out at another angle, and I'm not sure why it's not drawing there, but you get the picture. That is totally not right. The lines have to come out perpendicular to the surface. And then lastly, the more lines we draw, the stronger the field is. So if I were to take this one on the right and I add these lines here, then I could look at the two of these and say, this field on the right one is stronger than the field on the left because it has more lines associated with it. Okay, so out of positive into negative. Secondly, the lines always come out perpendicular. And thirdly, the more lines is the stronger field. So if you're looking at these, then we can see what's going to happen here. Now, they have to come out perpendicular, but once they come out, they're going to affect each other because what do two plus charges do? They repel. And so you see that in the lines where it creates this sort of, and I'm not going to be able to draw this very well, but it creates this sort of asymptote down the middle, to use a really nice math term, where the field gets close, 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 but never actually touches it. As opposed to if I have two charges that are the same, then or that are opposite, it will come out of the positive and then bend back into the negative. And technically speaking, these ones here, they come out and come all the way up and around. They just get really, really weak out here. And this one here, it goes all the way off the screen, all the way back around to the other side of the screen and comes on that way. But again, it just gets so weak on the outside that we don't usually draw it for that. So again, it's how do you know what are the two charges that are here? So take a moment and think about that. What are the two charges? Are they both positive? The answer would have to be no, because you have lines that are coming together here. So doesn't that mean that they are attracting, which means they've got to be opposites? Now, do you know which one is positive, which one is negative? And the answer to that is no, you don't really. You just know that they are opposite charges because those lines look very much like this bottom right one there. Okay, so properties of conductors in electrostatic equilibrium. There are 4 of these. So excess charges gather only on the outside of the surface, never the inside. So if I have a conductor here and they have the chance to go to the outside, they're all going to migrate to the outside of the surface. So picture this as a huge metal ball. This is a Van de Graaff generator. We're going to pull one of these out later and look at it. And if you may have seen it at like a Museum of Science and Industry where you put your hand on the ball and all your hair stands straight out. That's a Van de Graaff generator. We're going to play with one of those. Number 2, the electric field inside is 0. So it's 0 on the inside, is 0 everywhere on the inside. And you can kind of think through that. If I have a field that's coming one way on one side and a field that's coming the same way on the other side, then they will cancel out. Okay, so the third one, the electric field coming in or out of the conductor is perpendicular. You should know that one already. We just said that from the previous for drawing the field. So picture if I have all these negatives here that we had in that first picture, negatives here, then doesn't it make sense that all of my fields are going to be coming into the Van de Graaff generator because it's a negative charge? If it were positive charge, we would draw them going the opposite direction. And then lastly, on an irregularly shaped surface, the charge accumulates where it's the most pointiest, or where the radius of curvature is the smallest. So you can kind of think through this logically, that what the charges want to do is get away from each other. And the easiest way for them to get away from each other would be to jump off the surface. Well, picture if you're going to try and jump off of the roof, you're not going to stand in the middle of the roof. You're going to go to the edge of the roof where the radius of curvature is the smallest to jump off of it. That's kind of the same idea with the electrons. Now, lastly, but totally unrelated, is this idea of grounding. Grounding is a definition that it is the easiest path for the electrons to flow through to go back into the ground, to this infinite source of electrons. So if I walk up to an object that is charged and I touch it, remember contact is one of the ways you can charge an object, the electrons will flow from me and down through my feet into the ground, assuming I'm not wearing insulated boots or anything like that. And that's really what grounding is, where you are pulling the electrons back into the earth. So now, here we go. Let's do a sample problem. What is the electric field intensity of a 16 microcoulomb charged particle 5 centimeters away from the charge? So when I look at that, I say, hey, I have the charge of the object. Remember that this micro symbol is 10 to the negative 6th. I have this 5, which is centimeters, so I'm going to do 5 times 10 to the negative 2 meters to get it out of centimeters. And now that gives me a charge, and it gives me a radius, which means I'm going to have to use the kq over r squared equation. So think through, if I use the other one, F equals EQ, first off, nothing in the problem mentions a force. Secondly, we don't know what the electric field is, although that's what we're trying to find. And thirdly, this charge, though, isn't it the charge that's put into the field? It's not the charge causing the field, and that's why we would do this kq over r squared. So if we punch those numbers in, 9 times 10 to the 9th, 16 times 10 to the negative 6th, all over the radius 0.05, or 5 times 10 to the negative 2nd, and then squared, then we end up with an electric field of that 5.75 times 10 to the 7th newtons per coulomb. So next step, if I take a 5 microcoulomb test charge and put it at this spot, then how much force will needed to be exerted on it? So we can think through this two ways. Can't we do Coulomb's law that we had earlier, kq over r squared? We could do that. Or now that we found the electric field, can't we take that electric field from the previous problem and plug it in and put the test charge in for our Q, and notice that we get the exact same answers because the math is based off of the same thing. So here's another sample problem. It is a 1D problem that has 3 charges, and I think we're going to hold that off for another video. So remember, to summarize all of it, remember that electric field is the area around a charge that affects other charges. There are 3 different ways that 3 different rules that you have to use to draw an electric field out of positive into negative. It always comes out perpendicular, and more lines, stronger field. And then there are 4 properties of a conductor that you would use in order to solve in order to look at the different properties. When we go to solve for electric field, there are 2 equations that we would use, either F equals EQ or E equals KQ over R squared, and that all depends on which kind of charge you're given.